It's wonderful to have you here tonight. Before we set off, I would love to know where you're listening from. A quiet bedroom with the lights dimmed low, a softly humming train moving through the dark, a comfortable sofa wrapped in a warm blanket while the evening settles around you. Wherever you are, I hope you feel relaxed, unhurried, and ready to drift gently outward into the stars. If you enjoy these calm explorations and would like to wander through more sleepy science, a like and subscribe helps this little channel continue its slow orbit. And to everyone already subscribed, thank you. Your support keeps this peaceful corner of the cosmos glowing. Now I promise to do my best not to make tonight's topic too exciting, though we will be heading into deep space to visit planets so unusual and so quietly astonishing that they might keep your imagination awake just a little longer than planned. If that happens, at least you will drift off knowing why many planets wander the universe without a sun, why some worlds rain molten glass sideways, and why Earth is only one design among countless possibilities. So then, shall we begin? What exactly is deep space exoplanet exploration, and why has the universe turned out to be far busier, stranger, and more crowded with worlds than anyone once believed? The universe you know, the one lit by our familiar sun, and framed by 8 planets and a scattering of moons, feels complete and self-contained. A tiny solar neighborhood that seems tidy and intuitive. But in the early 1990s, astronomers began to look beyond that comforting boundary, with instruments more sensitive than any before. They expected almost nothing. A few rare discoveries if they were lucky. A quiet expanse of darkness. Instead, the cosmos offered something entirely different. Planets were everywhere. They orbited stars of every size. They drifted alone through the dark. They circled 2 suns, or sometimes 3. Some were wrapped in oceans hundreds of kilometers deep. Others glowed red beneath skies of evaporating rock. These worlds were invisible to the eye, far too faint and far too distant to see directly, but their presence revealed itself through the gentlest hints. A soft dimming of starlight here, a small rhythmic wobble there, subtle signals that, when interpreted with care, uncovered entire planetary systems hiding in the starlit dark. And the more astronomers looked, the more the universe seemed to overflow with planetary richness. Not dozens, not hundreds, thousands discovered so far, and far beyond that, likely billions upon billions waiting silently across the galaxy. Deep space was not empty at all. It was a vast and quiet garden of worlds. In this gentle journey we will drift through that cosmic garden slowly. There is no need to understand every detail or hold every fact in mind. We will move softly, one idea at a time, exploring how distant planets are found, what they may be made of, and what strange environments exist under suns far older or brighter than our own. So settle in, breathe deeply, and let your thoughts float outward for a while. Tonight, you're going to wander through a universe where nearly every point of light may shelter a family of worlds, and where the idea of Earth as something rare becomes only one possibility among countless others. Deep space can feel like an endless quiet, a darkness so wide and so still that it almost seems empty. When you look up at the night sky, the stars appear scattered and delicate, each one surrounded by a vast stretch of blackness. It is easy to imagine that the universe is mostly nothing, a great cosmic gulf with only a few bright points to interrupt the silence. But that impression, soothing as it may be, is not quite true. The calm darkness between the stars is not empty at all. It is only quiet because everything within it is so unimaginably far away. If you could drift outward from Earth and watch our home fade behind you, the familiar constellations would slowly lose their shapes, stretching apart as perspective changed. You would pass through regions where the closest star is trillions upon trillions of kilometers away, and those distances would grow larger still as you continued. Deep space is a place where distance becomes an ocean. Even the fastest spacecraft humanity has ever built would take tens of thousands of years just to reach the nearest star, moving steadily through a darkness that barely seems to change at all. The silence is not because there is nothing there. The silence is because everything is so widely spaced, so patient, so unwilling to hurry. Across this enormous gulf, light travels with perfect calm. A beam of starlight cast into the void will wander for years before brushing against anything solid. Planets, dust clouds, wandering fragments of rock, and the faint haze of gas that drifts between stars all sit scattered like gentle whispers within the dark. None of them glow on their own. None of them announce themselves. They simply exist, waiting quietly until light reveals them. And because most of them shine only by the faint light of distant stars, they remain hidden to the casual gaze. Deep space gives the impression of emptiness, not because the universe is bare, but because its inhabitants live in a darkness far deeper than our eyes can reach. Yet despite the quiet and despite the darkness, deep space is overflowing with worlds. For a long time, people imagined our solar system as a rare arrangement, perhaps even unique. It felt natural to assume that most stars were simply suns without planets, shining alone in the dark. But as astronomers looked more carefully, the opposite picture emerged. Planetary systems are not exceptions, they are the rule. Nearly every star you see in the night sky may host its own family of planets, circling steadily, silently, far too faint to be seen directly. They hide in the dark like tiny secrets, each one with its own story of heat and cold and atmosphere and history. The stillness of deep space makes the mind wander. It is difficult to grasp distances that stretch beyond anything familiar. You could line up every planet in our solar system from Mercury to Neptune and still not make a dent in the gulf between stars. The darkness between them is like a calm sea at night, stretching out endlessly in all directions. If you floated there, far from any source of light, the stars would shine around you like distant lanterns. You might feel suspended in an infinite room, one with no walls, no ceiling, and no floor. Only gentle pinpricks of brightness mark in places where suns burn, each with their own gravitational families. This quiet vastness is not threatening. It is serene in its scale. The universe is wide enough that everything has space to breathe. Gravity moves slowly out here, shaping the orbits of planets and guiding wandering debris with a patience beyond human experience. From the outside, planetary systems appear as delicate arrangements, each one a small island of motion within a sea of stillness. A star glows at the centre, its planets forming loops of lightless motion around it, circling year after year in a rhythm that continues whether anyone observes it or not. If you could pause time and walk across this cosmic sea, you might encounter planets of every imaginable type. Some would be enormous and stormy, some small and barren, some frozen entirely, others glowing with heat. And most would never be visible from afar, even to a keen pair of eyes under a perfect sky. They are concealed by distance, dimness, and the overwhelming reach of space. But they are there, waiting in the dark, countless and varied. The idea that deep space is empty fades once you understand how many planets occupy the universe. They are specks of possibility scattered across unimaginable distances. They hide behind starlight, they drift unnoticed, and they wait patiently for the rare moment when a telescope catches them in just the right way. The quiet between stars is not a void. It is a gentle curtain behind which countless worlds turn, orbit, freeze, burn, and drift. When you look up at the night sky and see the soft glow of a single star, you're likely looking at a system far richer than it appears. The dark space on either side of that star may contain planets, moons, debris fields, and clouds of material left over from ancient formation. The cosmic vastness is only quiet because it must be. Light needs time to travel, and worlds need space to orbit. The silence is part of the grandeur. And so, when thinking about deep space, it helps to imagine not an empty darkness, but an immense distance filled with hidden stories. Every faint speck of starlight may shelter companions we cannot yet see. Every stretch of darkness may conceal drifting worlds moving slowly with no one to witness them. The universe does not lack planets. It simply hides them well, wrapping them in lightless distances that soften their presence. This quiet vastness is the stage on which the search for exoplanets unfolds. A vast and gentle darkness, filled with far more than the eye can ever perceive. A calm ocean of space where worlds float like secrets waiting to be found. For most of human history, the idea of planets beyond our solar system lived only in imagination. Philosophers wondered about other worlds, storytellers dreamed about them, and astronomers speculated cautiously. But there was no evidence to confirm that anything existed beyond our familiar collection of planets circling the sun. When people looked at the night sky, they saw stars as points of light and assumed that was all they were. Distant suns, certainly, but suns that lived alone. To think otherwise required a bit of courage. After all, how could anyone prove that a faint speck of light was something more than a star? How could you show that an unseen companion was circling it? Early astronomers had their suspicions. In the 1800s, a few scientists wondered whether tiny wobbles in starlight might mean something was tugging on a star. But the instruments of the time were simply not precise enough to confirm anything. Measuring a star's position in the sky with the tools of that era was like trying to spot a grain of sand shifting on a distant beach through a fogged window. Even if a planet was there, its presence would be buried beneath noise, atmospheric distortion, and the limits of early telescopes. So the question lingered quietly for generations. Were there planets around other stars, or was our solar system a rare arrangement in a largely empty universe? Through the 20th century, astronomers refined their tools, building ever more sensitive photometers and spectrographs. They learned how to measure starlight with greater accuracy, studying subtle changes in brightness and motion. But progress remained slow. Stars are enormous, bright, and distant, while planets are small, dim, and overshadowed by their parent stars. Trying to detect a planet next to a star is like trying to notice a firefly circling a lighthouse. The firefly is there, but the lighthouse overpowers everything around it, washing away the faint signal you're trying to see. Even the closest stars were simply too bright compared to their planets to allow direct observation. For decades, many astronomers doubted the possibility of detecting an exoplanet with certainty. Even if planets existed by the billions, the universe did not make them easy to find. A planet does not shine with its own light. It reflects only a tiny fraction of the light falling onto it, and that reflected light fades into the dark long before it reaches Earth. Without a clear way to separate a planet's signal from its stars, the search remained a slow and delicate pursuit. Then came the 1990s, and everything changed. New generations of instruments arrived with sensitivity far beyond anything used before. These tools could measure the wobble of a star with astonishing precision, detecting movements so small that they would be invisible by any normal standard. A star with a massive planet tugging on it does not sit perfectly still. It shifts gently, moving in response to the gravitational pull of its orbiting companion. This shift is tiny, incredibly tiny, but detectable with careful methods. In 1995, astronomers found the first confirmed planet orbiting a Sun-like star. It was a moment of astonishment, not only because the detection was successful, but because the planet itself was unlike anything seen in our own solar system. It was enormous, roughly the size of Jupiter, but it orbited its star at a blistering pace, circling closer than Mercury circles the Sun. In just a few days, this planet completed a full orbit. It was a world so hot that its atmosphere would be blasted by intense starlight, a place where winds would roar endlessly under extreme temperatures. Its discovery was unexpected, almost shocking, and it forced astronomers to rethink their assumptions about what planetary systems could look like. What mattered most, however, was that the detection was real. A planet had been found not through imagination or speculation, but through careful measurement. A subtle wobble in starlight, interpreted through a new generation of instruments, had revealed a world more than 40 light-years away. And once one planet was discovered, more soon followed. The doors for discovery, long locked, opened with ease. Within a few years, dozens of exoplanets were identified. Within a decade, hundreds. And now, astronomers have found thousands, with many more candidates waiting to be confirmed. The breakthrough of the 1990s did more than expand our cosmic map. It changed our understanding of the universe entirely. Before this era, people tended to imagine our solar system as a typical example of how planets were arranged. After the discoveries began, that assumption faded quickly. Planetary systems turned out to be wildly varied. Some stars hosted planets larger than Jupiter in tight, rapid orbits. Others had systems of small rocky worlds. Some stars had no large planets at all, but seemed to hide tiny ones instead. And some stars had planets that appeared to be made of exotic materials, with temperatures and weather patterns almost beyond comprehension. Perhaps the most profound shift was the realization that planetary systems are not rare. They seem to be everywhere, scattered across the galaxy in vast numbers. Almost every star you see in the night sky may have planets orbiting it, each system with its own history, structure, and potential for hosting life. The universe, once thought to be mostly empty space punctuated by stars, now appeared to be a grand collection of worlds. The sheer scale of it all transformed astronomy from a study of stars into a study of systems, environments, and possibilities far beyond our own. Finding planets beyond our solar system was always going to be difficult. Stars are bright, planets are faint, and distances are immense. But the effort revealed something extraordinary. It showed that our cosmic neighborhood was never isolated, never unique, never alone. The early discoveries of the 1990s marked the beginning of a new era, one where humanity finally knew with certainty that worlds exist everywhere. They orbit quietly, they drift unnoticed, and they wait patiently in the dark. And all it took to reveal them was a tiny, almost imperceptible wobble in starlight, a gentle signal that changed our sense of the universe forever. Finding a planet you cannot see is one of the most delicate arts in astronomy. It is a little like trying to learn about a bird hidden inside a distant tree, by watching only the leaves it disturbs as it moves. Planets do not announce themselves. They do not glow. They do not shimmer in a way that separates them from the overwhelming brightness of their parent stars. Instead, they hide in the light, leaving behind only faint clues that something small and dark is circling far away. The key to discovering these invisible worlds is to pay close attention to the subtle behaviors of the stars they accompany. One of the most successful methods is called transit detection. This approach is astonishingly simple in concept, even though the tools needed to perform it are remarkably advanced. Imagine watching a single star very carefully for a long time. If a planet happens to pass directly between that star and the telescope observing it, the star will dim by a tiny amount. The planet casts a small moving shadow, reducing the starlight just enough for a sensitive instrument to notice. The star brightens again once the planet moves out of the way. This dip in light repeats with every orbit, creating a predictable rhythm. The amount of dimming is unbelievably small. For an Earth-sized planet passing in front of a Sun-sized star, the change is like removing only a few grains of sand from a pile the size of a truck and expecting someone on the other side of a vast field to notice the difference. And yet, astronomers can measure this change with extraordinary precision. Modern telescopes are designed to watch thousands of stars at once, detecting variations in brightness far smaller than anything our eyes could ever perceive. Transit detection tells astronomers several important things at once. It reveals that a planet exists, of course, but it also shows how large the planet might be. The deeper the dip in brightness, the larger the world blocking the light. The regular spacing between dimming events shows how long the planet's orbit takes. This rhythm of light becomes a quiet clock, ticking softly as the planet circles its star. From this simple pattern, entire planetary families can be sketched with surprising accuracy. Another powerful method is the measurement of stellar wobble. Although a star is far more massive than any planet orbiting it, it is not completely still. The gravitational pull of the planet tugs on the star, causing it to move in a small circle or ellipse. This motion is tiny, gentle, and far too small to see with the eye, but it affects the starlight. As the star moves slightly toward Earth, its light shifts in a measurable way. As it moves away, the opposite shift occurs. By tracking this back and forth pattern, astronomers learn not only that a planet exists, but also how heavy it might be. This wobble method is especially useful for finding large planets that orbit close to their stars. These planets may be completely invisible in images, but their influence on the star is unmistakable. The star becomes a messenger, announcing the presence of its unseen companion through these subtle movements. Even the light itself carries hints, stretching and compressing in a way that reveals the gravitational story unfolding around it. To measure any of these things, astronomers need instruments far more sensitive than anything used in ordinary observation. Telescopes designed for exoplanet hunting are not simply giant mirrors pointed at the sky. They are precise machines capable of measuring changes in starlight smaller than 1 part in 10,000. Some telescopes sit on mountain tops where the air is thin and clear. Others float in orbit above the atmosphere, where nothing disturbs the incoming light. They watch patiently, collecting small variations in brightness or motion, and translating them into signals of distant worlds. These instruments succeed not through dramatic images but through quiet and careful measurement. Most exoplanets were not discovered with sweeping photographs of glowing worlds. They were found through data, graphs, gentle dips in light, minute changes in starlight colour, patterns repeated over days, months, or years. In the hands of astronomers, these patterns become maps of places that will never be seen directly, at least not with present technology. Every detection is a small triumph. A tiny dip in starlight becomes evidence of a world hundreds or even thousands of light years away. One slight shift in a star's motion becomes proof that something is tugging on it from afar. Over time, these small discoveries accumulate, revealing a cosmos thick with planets of every size, temperature, and structure. The art lies not in seeing the worlds themselves, but in noticing how their presence reshapes the behavior of the stars. It is remarkable to think that most of what we know about exoplanets comes from the tiniest of clues: a barely noticeable change in brightness, a subtle shift in a star's colour, a rhythm of dimming that plays out faithfully across enormous distances. These signals whisper the existence of worlds that would otherwise remain unknown. They teach us that even when something is invisible, it can still leave a trace strong enough to decode. The telescopes that perform this work do so in silence. They stare at the sky for years, collecting streams of light from stars scattered across the galaxy. From these streams emerge discoveries that reshape our understanding of the cosmos. These instruments show that deep space is not a quiet emptiness, but a stage full of planetary systems, each one moving through its own graceful orbit. The art of finding invisible worlds is not magic. It is patience, precision, and the willingness to listen to the faintest changes in starlight. These clues may be delicate, but together they reveal a universe overflowing with hidden places, worlds orbiting quietly in the dark, worlds tugging on their stars, worlds darkening starlight by the smallest amount. Each discovery begins as a faint signal, and each one ends as proof that the universe is far richer and more crowded with planets than anyone once imagined. Starlight may look simple from a distance, a steady glow shining across the dark, but hidden inside that soft light is an extraordinary amount of information. Every ray that reaches Earth carries a record of the journey it has taken, brushing past clouds of gas, weaving through the atmosphere of a distant world, or passing unhindered through the emptiness of space. Light remembers where it has been. It arrives as a whisper of stories written in colours far too subtle for the unaided eye to see. When astronomers study starlight closely, they discover that it is far more than illumination. It is a cosmic message, encoded gently and patiently across unimaginable distances. When a planet passes in front of its star, some of the starlight shines directly toward us, unobstructed and unchanged, but a small portion of that light slips through the thin layer of gases surrounding the planet. As it does, the light is shaped by whatever chemicals it encounters. Certain gases absorb very specific shades, removing them from the star's glow. Others scatter the light or shift it slightly, leaving delicate impressions on the spectrum. Even though we cannot see this change with our eyes, it exists like a fingerprint. It is faint, fragile, and incredibly informative. By studying these tiny differences, astronomers can learn what a planet's atmosphere is made of without ever visiting it. To understand how this works, imagine shining a white light through a stained glass window. The window tints the light, allowing some colours to pass and blocking others. The final glow is shaped by the materials within the glass. In a similar way, a planet's atmosphere acts like a thin stained window around the world. Gases such as water vapour, methane, carbon dioxide, or oxygen absorb their own preferred colours. They leave behind gaps, tiny missing pieces in the light that reaches the telescope. These missing pieces form a pattern that reveals which gases sit in the atmosphere and in what proportions. The pattern is called a spectral signature, but despite the scientific name, the idea is wonderfully simple. Each gas leaves a unique mark. Once you learn to recognize those marks, reading a planet's atmospheric composition becomes like recognizing a familiar melody. The study of these signatures is delicate work. The differences in color are so small that no human eye could hope to notice them. Instead, astronomers rely on finely tuned instruments that can separate starlight into its individual shades with astonishing accuracy. A telescope may split the light from a single star into a long rainbow, stretching from deep red to violet. At first glance, this rainbow appears smooth, but with careful measurement, astronomers find narrow notches or dips, tiny places where light is missing. These notches are the clues. They are the places where the planet's atmosphere gently removed a piece of the starlight before sending the rest on its way. Each element and molecule has its own set of notches. Water vapor leaves one pattern, methane another, and oxygen a different one again. By comparing the observed rainbow with the patterns recorded in laboratories on Earth, astronomers can match the signature to the correct gas. In this way, a distant planet reveals its atmosphere piece by piece, molecule by molecule, even though the planet itself remains invisible. This ability feels a little like magic, but it is grounded in physics, chemistry, and an understanding of how light interacts with matter. The power of this method lies not in its drama but in its precision. It allows astronomers to detect gases present in tiny amounts. For example, if a planet has only a thin trace of water in its atmosphere, the starlight passing through will still show a faint mark where the water absorbed specific colors. This mark may be no wider than a hair's breadth on a stretched-out spectrum, yet it is enough to confirm the presence of water thousands of light-years away. The same technique can identify clouds, hazes, or even the likely temperature of the atmosphere. Light passing through a warm atmosphere contains slightly different patterns than light passing through a cold one. There is something poetic about learning so much from such subtle changes. We often imagine space exploration as a bold, dramatic undertaking, full of enormous rockets and distant journeys. Yet much of what we know about other worlds comes from quiet observation. A telescope sits in the darkness, collecting faint starlight. Inside that light are small clues about distant environments, and from those clues, entire landscapes begin to take shape in the mind. A world with a thick atmosphere rich in methane might appear hazy blue. Another with abundant water vapor may host clouds or oceans. Still, another with strange chemical combinations may be entirely unlike anything we know. Not all information is easy to capture. Sometimes the signal is too faint, the star too active, or the planet's atmosphere too thin. When this happens, astronomers must be patient, collecting more starlight over many orbits. A single set of measurements may not be enough, but dozens of orbits observed over months or years can slowly build a clearer picture. These long-term observations are acts of quiet persistence. Each piece of data fills in a small part of the whole. As telescopes become more advanced, the whispers in starlight grow easier to hear. New space observatories can detect finer details than ever before, splitting starlight with precision that would have seemed impossible only a few decades ago. These instruments allow astronomers to study atmospheres not only of large gas giants, but also of smaller, rocky planets similar in size to Earth. In some cases, the measurements become so sensitive that they hint at clouds, storms, or temperature variations across a planet's surface. The method is gentle but powerful, because it does not disturb what it studies. Light arrives naturally, shaped only by the universe itself. Astronomers simply receive it and read its patterns. This makes the technique invaluable, allowing the study of worlds that lie far beyond the reach of spacecraft. Even if no probe ever visits them, their atmospheres can still be known through the quiet language of starlight. When you picture starlight travelling across the galaxy, imagine it carrying a message about the world it passed through, written not in words but in colours and gaps and patterns. Astronomers learn to read this message with patience, curiosity, and careful instruments. And from this cosmic whisper, they uncover the nature of worlds that would otherwise remain forever unknown. When astronomers confirmed the very first planets beyond our solar system in the 1990s, they expected to find distant cousins of the worlds they already knew, perhaps something like Jupiter, sitting far out in a cold orbit, or rocky planets more or less similar to Earth, circling comfortably at moderate distances. What they did not expect was a family of planets so strange, so close to their stars, and so blisteringly hot that they seemed to defy the very principles of how planetary systems were thought to form. These were the hot Jupiters, enormous gas giants orbiting so tightly around their stars that they complete entire years in only a few days. A hot Jupiter is, at first glance, familiar in size. Many of them have masses close to Jupiter, and some are even larger, but everything else about them feels like it belongs in an entirely different universe. Instead of drifting patiently through a distant orbit, these giants circle incredibly close to their stars, sometimes closer than Mercury is to the Sun. Their days are scorched by unrelenting heat, and their nights may be only slightly cooler, depending on how well their atmospheres redistribute energy. If Jupiter lived in such a place, its beautiful pastel bands would not survive the extreme temperatures. Its atmosphere would swell, distort, and churn in ways that are difficult even to imagine. These tight orbits shocked astronomers because they contradicted long-standing theories. According to classical models of planetary formation, gas giants should form far from their stars, where icy materials are abundant enough to build the cores that attract thick envelopes of gas. Such planets should have wide, slow orbits, taking years to complete a single journey around their suns. Yet here were planets of similar mass and structure, orbiting at breakneck speeds, sprinting around their stars in only a handful of days. The discovery did not match the expectations, and so scientists were forced to reconsider how planets migrate over time. The extreme closeness of hot Jupiters to their stars creates environments unlike any in our own solar system. These planets experience temperatures that can soar to thousands of degrees, hot enough to melt metals and strip molecules apart. Their clouds may not be made of water vapour but of vaporized minerals. Some may have clouds of iron droplets or silicate particles, creating skies filled with glittering, scorching haze. Winds on these planets can reach unimaginable speeds, racing from the day side to the night side in a ceaseless attempt to balance the temperature difference. In some models, the winds move faster than the speed of sound, sweeping through the atmosphere in a constant roaring rush. Most hot Jupiters are thought to be tidally locked, meaning one side always faces the star while the other side lingers in perpetual darkness. The day side remains eternally heated, basking in unbroken starlight, while the night side stays in shadow. This creates extreme contrasts across the planet. The evening terminator, the region where day meets night, becomes a band of fierce atmospheric turbulence. Heat shifts around a planet in vast streams, and the atmosphere itself swells under the powerful starlight. Some hot Jupiters even appear larger than expected, as though the heat from their stars puffs them outward. Because hot Jupiters orbit so close to their stars, they are especially easy to detect. Their transits cause noticeable dips in starlight, and their gravitational pull creates larger wobbles in the star's motion. As a result, many of the first exoplanets discovered fell into this unusual category. This early sampling shaped the young field of exoplanet science. At first, it seemed as though the universe was filled mostly with these giant, overheated planets. But as more sensitive instruments became available, astronomers discovered that hot Jupiters are relatively uncommon. They merely appeared abundant because they were the easiest planets to find. Even though they are not the dominant type of planet in the galaxy, hot Jupiters have had an enormous influence on modern astronomy. Their existence demonstrated that planets can migrate significantly after they form. Instead of staying in the distant icy regions where they begin their lives, some planets move inward over millions of years, spiraling closer and closer to their stars. This migration reshapes entire planetary systems, disturbing smaller planets and altering orbital structures. Theories of how solar systems evolve had to be rewritten to account for this surprising behavior. Hot Jupiters also provided early opportunities to study planetary atmospheres in detail. Their size, combined with their close orbits, makes them perfect candidates for atmospheric analysis. When they pass in front of their stars, a significant amount of starlight travels through their atmospheres before reaching Earth. This allows astronomers to measure the chemical composition of these scorching worlds, detecting sodium, water vapor, and even hints of exotic molecules. In some cases, the brightness of the star drops slightly as the planet passes behind it, allowing scientists to estimate how much heat the planet emits on its own. As a result, hot Jupiters became laboratories for understanding atmospheric physics under extreme conditions. Their observations helped refine techniques now used to study smaller, cooler planets that may have more Earth-like properties. In a sense, these fiery giants served as training grounds for the methods astronomers needed to examine more subtle worlds. There is also something deeply captivating about imagining such planets, a world the size of Jupiter orbiting so close to its star that a single year is shorter than a human work week feels almost theatrical. The skies would be bright beyond anything on Earth. The star would dominate the horizon. The atmosphere would be a swirling cauldron of heat, pressure, and violent winds. It is a place where the rules of weather, climate, and chemistry operate on scales and intensities far beyond anything familiar. Hot Jupiters remind us that the universe is not limited to the tidy, well-spaced arrangement found in our solar system. Planetary systems can be wild, unpredictable, and extraordinarily varied. These fiery giants were some of the first exoplanets we ever found, and their unexpected presence changed the direction of astronomy. They forced scientists to expand their models, rethink long-held assumptions, and approach the search for new worlds with an open mind. Their strange lives, so different from anything in our own neighborhood, helped reveal that the cosmos is full of surprises, waiting quietly in the starlight. Super-Earths are one of the most intriguing surprises to come out of exoplanet research, partly because they seem to be everywhere except in the one place you might expect to find them, our own solar system. Despite the name, a super-Earth is not necessarily a larger or more dramatic version of Earth. Instead, the term simply describes a planet that is bigger than Earth and smaller than Neptune. That is all. A broad, flexible category with room for dozens of possibilities. Some super-Earths may be rocky, some may be covered in thick atmospheres, Some may be water-rich, or even ocean-dominated. The name does not imply that they are Earth-like, only that they fall into a size range that sits comfortably between familiar worlds. What makes them so fascinating is that they appear to be extremely common across the galaxy. Many of the exoplanets discovered so far fall into this middle category, larger than Earth, but not quite large enough to become gas giants. In fact, super-Earths may be one of the most common types of planet in the Milky Way. Yet for reasons that remain uncertain, our solar system contains none. We have small rocky planets like Mercury, Venus, Earth, and Mars. We have large gas giants like Jupiter and Saturn. We have ice giants like Uranus and Neptune, but nothing in between. It is as though the solar system skipped an entire category that the rest of the galaxy embraces freely. This absence raises interesting questions. Why does our solar system lack a super-Earth, when so many other star systems seem to host them? One leading idea suggests that the early solar system may have formed one or more of these mid-sized planets, but that they migrated inward or outward and were later lost, perhaps falling into the Sun or being flung into interstellar space by gravitational interactions. Another possibility is that the region where super-Earths tend to form was disrupted in our system, preventing them from taking shape at all. Whatever the explanation, it appears that our planetary neighbourhood is something of an oddity. The diversity among super-Earths is astonishing. Some may be only slightly larger than Earth, while others approach the size of Neptune. A planet at the smaller end of the category might have a rocky surface, volcanic activity, mountains and oceans under a familiar sky. A planet at the larger end might have a thick, crushing atmosphere made of exotic gases, with pressures far beyond anything comfortable for human life. Other super-Earths might be covered entirely by water, turning them into world-spanning oceans with no visible land. These ocean planets could have deep layers of high-pressure ice beneath the water, with warm interiors and complex interactions between heat, pressure, and chemistry. Some super-Earths orbit close to their stars, basking in heat that can turn their surfaces molten. These lava worlds may have rivers of melted rock and glowing volcanic plains. Others orbit at more comfortable distances, with temperate climates and atmospheres that could potentially support life. In some cases, the atmospheres of super-Earths appear to be enriched with water vapour, hydrogen, or a mix of gases that produce unusual cloud patterns. Because the category is so broad, each super-Earth becomes its own mystery, its own story waiting to be deciphered. One of the reasons super-Earths attract so much interest is that their size makes them easier to detect. A super-Earth passing in front of its star blocks more light than a smaller planet would. A super-Earth tugging on its star produces a stronger wobble. These characteristics make them highly visible to transit surveys and radial velocity studies. As a result, scientists have been able to gather a great deal of data about them, creating a large and growing catalogue of strange intermediate-sized planets. Their size also puts them at an interesting crossroads in planetary science. A slightly larger planet than Earth might be able to hold onto a thicker atmosphere, altering its climate, surface chemistry, and potential for habitability. A planet closer to the upper end of the category may experience such intense pressure that its atmosphere becomes opaque, layered, and wildly different from anything known on Earth. Understanding how these atmospheres form and behave helps scientists refine their models of planetary evolution. Another key question concerns composition. A planet just a few times more massive than Earth might still be mostly rock, but its interior properties would be different. Higher pressures could produce denser cores, more vigorous volcanic activity, and stronger magnetic fields. On a larger super-Earth, the boundary between rock and gas becomes less clear. Some planets may have thick upper layers of hydrogen or helium. Others may have deep oceans that interact with the planet's mantle in complex ways, creating chemistry that could either support or hinder life. The fascination also comes from imagining what a super-Earth might feel like if you were able to stand on it, even though most would be far too extreme for such an experience. On a smaller, rocky super-Earth with a breathable atmosphere, the gravity might be stronger, pulling everything down a little more firmly. Mountains might not rise as high, because rock would be less able to support tall structures under increased pressure. The sky might appear different, coloured by the specific gases present. Weather could be more intense, shaped by the planet's greater mass and thicker atmosphere. Everything familiar would have a slightly altered character. Super-Earths challenge the idea that Earth is a typical example of a rocky planet. Instead, Earth appears to be on the smaller side of the rocky spectrum, missing the additional mass and complexity found in many other systems. This raises profound questions about habitability. Is Earth uniquely suited for life because of its moderate size, or would a slightly larger world be equally or even more hospitable? Would thicker atmospheres help regulate climate more effectively, or would they trap too much heat? These are the kinds of questions scientists hope to answer as new telescopes gather more detailed data. Part of the charm of super-Earths comes from their diversity and their abundance. They remind us that the universe does not follow a single blueprint for building planets. Instead, it experiments on grand scales, creating worlds that fill every possible niche. From molten surfaces to deep oceans, from thin atmospheres to dense swirling skies, super-Earths offer a glimpse into the many ways a planet can take shape. Their absence in our solar system does not make them rare. It simply makes our home system a little more unusual than expected. As astronomers continue to study these planets, the mystery deepens. Why are they so common elsewhere? Why did our solar system avoid forming one? And what hidden landscapes lie beneath their swirling atmospheres? Super-Earths invite curiosity not because they are familiar, but because they challenge our understanding of what a normal planet truly is. They remind us that the galaxy is filled with worlds stranger and richer than anything found in our immediate neighbourhood, and that sometimes the most intriguing mysteries begin with the things that are missing. Ocean worlds are some of the most peaceful and mesmerizing planets imagined in modern astronomy. These are worlds with no continents, no islands, and no exposed land at all. Instead, they are wrapped entirely in water, their surfaces stretching into uninterrupted global seas. If you were to drift down toward one of these planets, you would see no familiar outlines of coastlines. Only endless blue, curving gently around the sphere and glimmering beneath the light of its distant sun. These ocean planets vary widely in temperature, composition, and depth, but they share the same defining feature. Water dominates everything. On Earth, the oceans cover a little more than 2/3 of the surface, and even that is enough to shape the climate, the weather, and the chemistry of our world. On an ocean planet, the sea covers 100%. The ocean could be shallow in some cases, perhaps only a few kilometers deep. In other cases, it may reach extraordinary depths. Some water worlds may have oceans stretching hundreds of kilometers downward, so deep that the pressures at the bottom would be far greater than anything found in the deepest trenches on Earth. These high-pressure conditions can form layers of exotic ice, solid not because of cold temperatures but because the weight of the water above forces the molecules into structured forms. The temperature on an ocean world depends heavily on its distance from its star. A warm ocean planet may have gentle waves and bright sunlit shallows. A colder one could be covered by a crust of ice, with a hidden ocean flowing beneath the surface, kept warm by internal heat. Light behaves differently on such planets. Near the surface, the sea may glow with scattered sunlight. Descend only a short distance, and the world becomes dim. In the deepest regions, the ocean falls into complete darkness, lit only by whatever internal glow the planet may produce. The quiet and the stillness of these depths create an environment unlike any surface landscape. The idea of life in these oceans is particularly compelling. On Earth, life began in water. The earliest organisms lived in warm, shallow seas before evolving into more complex forms. Many deep-sea creatures today thrive in environments without sunlight, relying instead on chemical energy from the planet's interior. These facts make ocean planets natural candidates when astronomers search for alien life. A world dominated by water provides a stable environment, rich in potential chemistry, shielded from harsh radiation, and capable of sustaining cycles of heat and nutrient movement. Even if the planet is locked beneath a thick layer of ice, the ocean below may remain warm and active, creating a hidden ecosystem similar to the subglacial oceans on moons like Europa. Some ocean planets might have atmospheres filled with water vapor, creating thick clouds and intense storms that circle the globe. Others might have thin atmospheres, allowing starlight to penetrate deep into the ocean. If the planet orbits close to its star, its waters may be warm and energetic, with powerful winds stirring the surface. If it orbits farther away, the world may be calm and cold, its ocean moving slowly under a canopy of ice. Each variation presents a different set of possibilities for planetary science. The chemistry of these oceans could be remarkably diverse. A planet with a rocky mantle beneath the water would allow minerals to dissolve into the ocean, providing building blocks for complex chemistry. Hydrothermal vents on the ocean floor could release heat and nutrients, creating hotspots where life might emerge or thrive. On planets with extremely deep oceans, the high-pressure ice layers could trap heat below them, insulating the lower waters and creating distinct layers of temperature and chemistry that interact in surprising ways. Understanding ocean worlds teaches astronomers how water behaves on planetary scales. Studying them also helps refine theories about how planets form and evolve. For example, some super-Earths may become ocean planets if they form with abundant water, or if their early atmospheres collapse, allowing vapor to condense into global seas. Other worlds may gain their oceans later through comet impacts, or the gradual release of water from their interiors. By examining these processes, scientists can better understand why Earth has oceans and how common similar environments might be. Water worlds are scientifically exciting because they push the boundaries of what a planet can be. They demonstrate that not all habitable environments require Earth like land and sky. Life, if it exists elsewhere, may thrive in places that look nothing like our home. The calm, endless waters of an ocean planet present both comfort and mystery. Comfort, because water is a familiar and life-supporting substance. Mystery, because the vastness of these global seas hides everything from geology to chemistry to the possible presence of life beneath their surfaces. It's fascinating to imagine standing at the edge of an ocean that has no shore. The horizon would be unbroken in every direction. Waves would move gently or fiercely depending on the climate of the planet. The atmosphere might carry the scent of unfamiliar chemicals, or the calm stillness of cool vapor. And beneath your feet, the water could extend downward for unimaginable distances, hiding layers of ice, rock, or heat, born currents that have never seen the light of a star. These planets also remind us of the adaptability of water, a substance that can create worlds as tranquil as Earth's shallow seas, or as extreme as high-pressure ice buried beneath a crushing ocean. They show that water is not a fragile rarity, but a universal ingredient capable of shaping entire planetary systems. Studying ocean planets enriches our understanding of habitability and widens our sense of where life might emerge. Ocean worlds, with their endless horizons and hidden depths, capture both scientific curiosity and human imagination. They stand as reminders that the galaxy contains environments far stranger and more beautiful than anything we have seen on Earth, and they invite us to keep exploring, listening to the quiet signals from distant stars that hint at the presence of vast, rolling seas on planets we have yet to fully understand. Weather on distant planets is a reminder that nature's imagination stretches far beyond anything experienced on Earth. Our own atmosphere can be dramatic at times, with hurricanes, lightning, and swirling clouds, but compared to the wild conditions on certain exoplanets, Earth's storms might seem almost polite. Across the galaxy, winds roar at speeds that would shred any earthly structure. Temperatures swing between extremes far beyond our comfort, and rains fall not as water, but as molten minerals or droplets of glass. These alien weather systems are not just curiosities. They reveal the physics that shape each planet and provide insight into how atmospheres behave under conditions completely unlike those found here. When astronomers first began detecting atmospheric signals from exoplanets, they quickly realized that alien weather could be astonishingly varied. On hot Jupiters, where searing temperatures dominate the day side, the upper atmosphere may reach thousands of degrees. In such heat, molecules can break apart only to reform when carried to cooler regions by fierce winds. These winds can race around the planet in only a few hours, flowing from the scorching day side toward the night side at speeds faster than sound. The entire atmosphere becomes an immense conveyor belt of heat, constantly trying to distribute energy around the globe. These winds arise because hot Jupiters are tidally locked, showing one face to their star at all times. While the day side endures endless heating, the night side remains in eternal shadow. The contrast creates a remarkable cycle, in which gases rise rapidly on the illuminated side, sweep over the terminator into darkness, cool, and then sink. This cycle repeats continuously, driving atmospheric currents on scales far larger and more intense than anything on Earth. In such environments, storms may be global in extent, stretching across entire hemispheres without interruption. In some extreme cases, exotic materials become part of the weather. On certain exoplanets, temperatures are high enough to vaporize silicate rocks. These materials form clouds just as water vapor forms clouds on Earth. When these mineral-rich clouds cool, they condense and fall as rain, though not the kind that gently taps against a window. Instead, the droplets may be molten glass or flakes of vaporized rock, drifting downward in shimmering sheets. On other planets, metals like iron may evaporate on the day side, forming clouds that later condense on the cooler night side, falling as tiny metallic droplets. These mineral rains demonstrate how temperature and composition work together to create atmospheric cycles that feel both fantastical and deeply logical. Not all alien weather is scorching. Some exoplanets orbit far from their stars, locked in deep cold. On these frozen worlds, clouds may form from methane or nitrogen, and temperatures drop low enough to freeze gases that are liquids or vapors on Earth. Winds on such planets may be slow and dense, with thick layers of atmosphere moving sluggishly over icy surfaces. Storms may build slowly, sustained by subtle variations in heat, rather than dramatic bursts of energy. Even in these quiet regions, the interplay between temperature, chemistry, and pressure creates complex weather patterns. The colour of a planet's atmosphere can also reveal clues about its weather. Some exoplanets appear deep blue not because of oceans, but because of scattering in hydrogen-rich atmospheres. Others may appear red or yellow due to clouds of exotic particles. If the atmosphere contains large amounts of dust or hazes, the sunlight passing through it will change in colour, tinting the planet when viewed from afar. These visual clues help astronomers infer whether a planet has thick clouds, storms, or layers of haze suspended high in the sky. In many cases, weather provides a window into a planet's internal heat. Some planets glow with more warmth than their stars alone can explain. This extra heat must come from within, possibly from gravitational compression or tidal forces that squeeze and stretch the planet. These internal processes can drive atmospheric motion, generating winds, affecting cloud formation, and shaping long-term climate. On worlds with strong tidal forces, the heating may be uneven, producing atmospheric patterns unlike anything on planets with stable orbits. Studying alien weather teaches astronomers how atmospheres function under different gravitational strengths. A planet much larger than Earth may have a thick atmosphere with a high escape velocity, meaning gases that would drift away from Earth remain securely trapped. This can lead to enormous storms that persist for long periods, sustained by the sheer volume of gas available. Conversely, a smaller planet may struggle to hold on to its atmosphere at all, with strong stellar winds gradually eroding it over time. These factors influence everything from cloud formation to the likelihood of rainfall. Weather also interacts with a planet's chemistry in intricate ways. On a world rich in carbon compounds, sunlight might trigger chemical reactions that create dark hazes, altering the temperature of the atmosphere and affecting how much heat escapes into space. On a planet with abundant volcanic activity, eruptions could inject gases into the atmosphere, shaping long-term climate and weather cycles. Even on planets without solid surfaces such as gas giants, internal storms can rise and fall through the layers, merging or breaking apart like colossal, drifting towers of turbulence. One of the most astonishing features revealed by atmospheric studies is the persistence of storms on giant planets. Some exoplanets may host storms that last years or even centuries, supported by deep reservoirs of energy and complex layering of gases. These storms can reach sizes larger than Earth, swirling in whirlpools of heat and colour. Observing such storms helps scientists understand how energy flows within massive atmospheres and how rotation, sunlight, and internal heat combine to create long-lived weather systems. Alien weather reveals the diversity of the universe in ways that go beyond simple temperature or atmosphere composition. It shows how physical laws express themselves differently under extreme conditions. It illustrates how clouds, winds, and rain adapt to environments that stretch the limits of imagination. And it reminds us that weather, no matter where it occurs, is always a dance between heat, pressure, motion, and chemistry. Thinking about the weather on distant planets offers a gentle reminder that the universe is full of patterns waiting to be recognized. Even in the most extreme environments, nature follows rhythms. Winds blow, clouds form, storms rise and fade. These familiar processes unfold on worlds that look nothing like Earth, yet they share the same underlying principles. Studying these patterns not only deepens our understanding of the cosmos, but also highlights the remarkable adaptability of atmospheric physics across the galaxy. Planets that orbit more than one sun belong to some of the most evocative corners of the galaxy. These are worlds where the sky is never quite the same from one moment to the next, where light arrives in shifting colours and directions, and where dawn and dusk can come twice in a single day. Multi-star systems are far more common than many people realise. In fact, a large portion of the stars in our galaxy live not as solitary objects like the Sun, but as pairs, triples, or even larger families held together by gravity. These systems create planetary environments that feel both familiar and dreamlike, shaped by the delicate pull of multiple suns. In a system with two stars, the suns may orbit each other closely, forming a compact pair, or they may drift far apart, moving slowly through space while remaining bound by their shared gravity. Planets in such systems can behave in several ways. Some orbit only one of the stars, remaining relatively stable while the companion star circles at a distance. Others orbit both stars together, tracing wide loops around the pair as if circling a single gravitational centre. The exact pattern of motion depends on the masses of the stars, their separation, and the initial conditions under which the planet formed. Gravity in these systems creates complex and elegant motion. A planet circling a pair of stars must follow an orbit that avoids being pulled too strongly in either direction. If it strays too close to one star, the gravitational tug becomes unbalanced. If it moves too far out, the orbit may become unstable. Yet nature finds ways to produce stable paths. These orbits can be surprisingly smooth, allowing planets to maintain long-term stability even in the presence of constantly shifting forces. In some systems, the planet feels the stars as a single combined mass, making its orbit more predictable. In others, the gravitational landscape changes gradually as the stars move around each other, leading to slow variations in temperature and light. The light on such a planet would be unlike anything experienced on Earth. Imagine standing on a rocky plain and watching two suns rise at slightly different angles. One might be bright white, the other a warmer orange. Their combined glow would cast overlapping shadows, creating subtle patterns on the ground. Depending on their positions, the light could appear sharper or softer, creating hues that shift gently throughout the day. As the suns move through the sky, the brightness would ebb and flow. If one sun sets while the other is still above the horizon, the world would be bathed in a dim, warm glow rather than falling into full night. In systems where the stars orbit each other closely, the planet may experience periods where one sun eclipses the other, briefly dimming the sky. A day might contain moments of sudden cooling or warming as one star passes behind the other or moves in front. The cycle of light would feel rhythmic, almost musical, shaped by the dance of the stars rather than the simple rotation of a single sun. On planets orbiting a wider pair, the changes might unfold more slowly. Over long spans of time, the distances between the planet and each star might shift slightly, causing gentle variations in climate. Seasons could be influenced not just by the tilt of the planet's axis, but also by the positions of the stars themselves. In extreme cases, a world might experience periods of double summer or double winter as the stars align in different configurations. The question of whether life could adapt to these changing environments depends on the stability of the system. If the planet's orbit is steady and the variations in light and temperature are not too extreme, life could certainly find ways to thrive. Plants, for example, might evolve to take advantage of the different wavelengths of light offered by each sun. Some organisms might become more active during the brighter phases of the cycle, while others rest when the light becomes too intense. Animal life, if it existed, could synchronize its behavior with the rhythms created by the double or triple sunrise and sunset. Even on Earth, countless species adapt to complex light cycles, from polar regions with months of sunlight to deep sea environments with almost none. Multi-star systems also raise interesting questions about habitability. A planet receiving light from two suns may enjoy a warmer climate, increasing the size of the habitable zone where liquid water can exist. In some cases, this could make planets more likely to support life. On the other hand, the variability of light might create challenges, especially if the stars differ drastically in brightness or temperature. The delicate balance between too much heat and too little becomes more complex when multiple stars contribute to a planet's energy. Despite these challenges, planets in multi-star systems are not as rare as once thought. Astronomers have discovered several worlds that orbit two stars, and simulations suggest that many more may exist in stable orbits. These discoveries have expanded our understanding of how planetary systems form. Instead of assuming that planets require a single, calm star like the Sun, scientists now know that planets can form and thrive in environments shaped by the combined influence of two or more suns. For those who enjoy imagining alien landscapes, multi-star planets offer some of the most striking scenes. A horizon glowing with twin dawns, shadows stretching in multiple directions, nights lit by one sun while the other rests, skies tinted with unusual colours as different wavelengths of light blend. Even the passing of time might feel different, marked not by a single cycle of day and night, but by overlapping patterns of brightness and shade. The beauty of these worlds lies in their variety. Some may be rocky and familiar, others gas giants with swirling clouds, reflecting two sources of light. Some may support stable climates ideal for life, while others orbit too chaotically to sustain anything for long. But each one is shaped by the graceful gravitational dance of its suns, and each reveals something new about the creativity of planetary formation. Planets with more than one sun remind us that the cosmos is not limited to the simple arrangements we see at home. Nature builds systems filled with intricate motion, blending stability and variation in ways that feel almost artistic. These worlds expand our sense of what a sky can look like and what a day can be, inviting us to imagine life under the shifting glow of multiple suns. Rogue planets drift through the galaxy without the warmth or guidance of a parent star. They do not circle a sun. They cast no neat orbital path, and they follow no predictable year. Instead, they wander freely through the dark, travelling along slow, solitary routes shaped only by gravity and the lingering momentum from whatever event set them loose. These planets move through space like quiet travellers, unlit and unbound, slipping between the stars in almost perfect silence. Their existence reminds us that not all worlds belong to neat, orderly systems. Some are loners from the start, and others are cast out from the families in which they once formed. A rogue planet can emerge in several ways. Some may form on the outskirts of young planetary systems where gravitational interactions are chaotic. In the early stages of formation, planets and smaller bodies jostle for space while the system settles into stable arrangements. A particularly strong gravitational tug from a larger neighbour can fling a smaller planet outward at great speed, sending it into an escape trajectory. Once free from the gravitational pull of its star, the planet becomes a wanderer, moving endlessly through interstellar space. Other rogue planets might have been captured temporarily by passing stars before being flung out again. or they may have formed directly in the cold depths of space without ever belonging to a stellar system. In such cases, they arise from collapsing clumps of gas and dust too small to ignite into stars but large enough to form planetary bodies. Whatever their origin, the result is the same: a cold, dark world adrift in the galaxy, carried along by gravity alone. On the surface, a rogue planet might seem like the loneliest object imaginable. With no sun to warm it, you could picture it as a frozen, lifeless sphere drifting through absolute darkness. But the truth is far more interesting. Even without sunlight, a rogue planet can generate warmth from within. During planetary formation, heat becomes trapped in the core, and some planets continue releasing this internal heat for billions of years. Radioactive elements inside the mantle can also provide a slow but steady source of warmth. If the planet is massive enough and has a thick atmosphere, that heat can remain insulated, creating a surprisingly stable environment. Imagine a rogue planet with a deep ocean buried beneath a thick shell of ice. The ice insulates the ocean, trapping heat from below. Hydrothermal vents on the ocean floor could release warm, mineral-rich water, just as they do on Earth. Even though the planet receives no sunlight, life could theoretically exist around these vents, feeding on chemical energy rather than light. This is not mere speculation. On Earth, entire ecosystems thrive in the darkness of the deep ocean, completely independent of the sun. If such life can emerge here, it is at least plausible that similar systems might occur on rogue worlds drifting through interstellar space. A rogue planet with a dense atmosphere might even have a faint glow. Heat leaking from its interior could warm the atmosphere enough to create a dim infrared emission. To human eyes, this would still look like complete darkness, but to sensitive telescopes, the planet might reveal itself as a soft, warm shade against the cold background of the universe. Detecting these planets is extraordinarily difficult, but not impossible. A few candidates have already been identified, suggesting that rogue worlds may be common. Some estimates propose that there could be more rogue planets in the galaxy than stars, drifting silently between the systems like seeds blown across a cosmic field. Because they do not orbit stars, rogue planets experience an uninterrupted night. If you stood on the surface, the sky would be a perfect black dome filled with stars, far sharper than anything visible from Earth. With no atmosphere scattering light and no sun dominating the view, the stars would appear bright and still. The Milky Way would stretch across the sky in a glowing band. The silence would be profound, broken only by the faint sounds of the planet itself, shifting or cracking as it cools over time. The mystery of rogue planets is not just about how they form or what conditions they might have, it is also about what they represent. They challenge the assumption that planetary worlds must be tied to stars. They broaden the definition of what a planet can be, and they invite questions about how many types of hidden environments may exist in the vast spaces between stellar systems. A rogue planet could drift for millions of years without passing near another star. Yet during that time, it remains a complete world with its own geology, atmosphere, and potential for life. Astronomers hope to learn more about rogue planets as observational techniques improve. Instruments that detect faint heat signatures may one day map these wanderers more precisely. Gravitational microlensing, a technique in which a rogue planet briefly bends the light of a background star, allows the detection of planets that would otherwise remain invisible. Each discovery adds another piece to the puzzle, expanding the picture of a galaxy filled not only with orderly solar systems but also with solitary travellers. The image of a rogue planet drifting through darkness may feel haunting, but there is a quiet beauty to it as well. These worlds move with calm certainty, unhurried by the cycles of day and night. Their journeys are shaped by ancient forces, their destinations unknown. In a universe filled with activity, explosions, and bright starry regions, rogue planets offer a soft, contemplative reminder of the stillness that exists between the lights. They drift peacefully, carrying their own warmth through the cold, showing that even in the vastest darkness, a world can remain whole. The idea of the habitable zone has a peaceful simplicity to it. It is often described as the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold. A gentle middle ground. If a planet orbits within this zone, water could remain in its liquid state rather than boiling away or freezing solid. Since water is essential for life as we know it, the habitable zone is the first place astronomers look when searching for worlds that might be capable of supporting biology. But this simple definition hides a great deal of complexity. Being in the habitable zone does not guarantee that a planet is truly habitable. A world may orbit at the perfect distance from its star and still be far too dry, too toxic, too barren, or too unstable to support life. The temperature on a planet's surface depends not only on its distance from the star, but also on its atmosphere, its rotation, its chemistry, and even its geological activity. A thick atmosphere can trap heat, warming a planet that would otherwise be cold. A thin atmosphere can do the opposite, allowing precious warmth to escape. Two planets in the same habitable zone may experience completely different climates. Earth is often used as the template for habitability because it is the only place where life is confirmed to exist. It sits comfortably in the Sun's habitable zone, and its atmosphere maintains a temperature balance that keeps water in liquid form across much of the surface. But Earth has many other factors that work in its favour. A magnetic field protects it from harmful radiation. Plate tectonics circulate nutrients and help regulate carbon dioxide levels. The presence of oceans stabilizes climate and supports a vast network of chemical reactions essential for life. Simply being in the right orbit would not have been enough without all these additional processes working together. When astronomers discover a planet within the habitable zone of a distant star, they view it as a promising candidate, not as a final answer. The next step is to determine what kind of atmosphere the planet has. If the atmosphere is too thick and filled with greenhouse gases, the planet may become a scorching world similar to Venus, even if it lies within the habitable zone. If the atmosphere is too thin, the planet may resemble Mars, where water once flowed but later vanished into space as the air gradually escaped. Chemistry plays a crucial role in shaping a planet's destiny. The balance between heating and cooling is delicate. A planet absorbs energy from its star and releases some of that energy back into space as heat. The rate at which this happens depends on the gases in the atmosphere, the reflectivity of clouds or ice, and the surface composition. A planet covered in bright ice will reflect much of the incoming light, keeping the surface cold. A planet with dark oceans or rock will absorb more light, warming more readily. Even small differences can lead to significant changes over geological timescales. The size and type of the star also influence the habitable zone. Larger, hotter stars have wider zones but shorter lifespans, which may not give life enough time to develop. Smaller, cooler stars have narrow habitable zones close to the star, raising questions about whether planets in these regions can remain stable. Close orbits may expose a planet to strong stellar flares or tidal locking, where one side always faces the star and the other remains in perpetual darkness. Life could still exist under such conditions, but it would need to adapt to environments very different from Earth. Astronomers search for signs of life by analysing the light that passes through a planet's atmosphere during a transit. If certain gases are present in unusual combinations, they may be indicators of biological activity. For example, oxygen and methane together would be difficult to maintain without something replenishing them. On Earth, plants and photosynthetic organisms continuously produce oxygen. Methane comes from a variety of natural sources, including microbial life. A distant telescope detecting both gases on an exoplanet would have strong reason to investigate further. Another promising sign is the presence of water vapor. Water is a versatile solvent that supports many chemical reactions associated with life. If starlight filtered through a planet's atmosphere reveals traces of water, it suggests that the planet may have clouds, seas, or even rain cycles. However, water vapor alone does not confirm habitability. It is simply one piece of a larger picture that must be assembled carefully. Some researchers also study the colors of light reflected from a planet's surface. Vegetation on Earth, for example, reflects light strongly in the near-infrared, a characteristic known as the red edge. If a similar signature appeared on another planet, it could hint at large-scale biological processes. The interpretation of such signals requires caution, as non-biological materials can sometimes mimic these patterns. Still, these subtle clues offer hope for identifying worlds with thriving ecosystems. The idea of habitability extends beyond the surface. A planet with a frozen exterior might still contain liquid water below, warmed by internal heat or tidal forces. Life in these deep oceans could exist without access to sunlight, feeding on chemical energy from hydrothermal vents. This possibility expands the definition of habitable environments far beyond the traditional notion of surface oceans under a sunlit sky. The search for life hinges on understanding these details. A planet in the habitable zone is not automatically a second Earth. It is simply a world with potential. The next steps involve studying its atmosphere, chemistry, and long-term stability. In many cases, astronomers must gather data slowly, orbit by orbit, as light filters through the atmosphere or reflects off the surface. Each measurement adds another piece to the puzzle. The habitable zone remains a useful guide, a gentle starting point for exploring the countless worlds scattered across the galaxy. But the hope for life depends on far more than distance from a star. Chemistry, climate, magnetism, and geological activity all play essential roles. As our tools grow more powerful, the picture becomes clearer. Planets that once seemed lifeless may reveal hints of water or surprising atmospheric compositions. Others may show conditions far too extreme to support biology. The search for habitability is ultimately a search for balance, a balance of temperature, chemistry, and energy that allows complexity to arise, a balance that has been achieved here on Earth and perhaps on many other worlds waiting quietly in the light of distant suns. Alien atmospheres are among the most revealing clues available to astronomers studying distant worlds. A planet's atmosphere acts like a diary of its history, recording everything from volcanic eruptions to chemical reactions to past interactions with starlight. Even when a planet cannot be seen directly, its atmosphere can often be detected and analysed from afar. The air surrounding a world absorbs and scatters light in distinctive ways, leaving behind signals that are subtle yet incredibly informative. By reading these signals, astronomers can learn what the atmosphere is made of, how thick it is, and what processes shape its chemistry. Detecting an atmosphere usually begins with observing how starlight changes when a planet passes in front of its star. During a transit, a small fraction of the star's light filters through the thin layer of gases around the planet. The atmosphere leaves delicate fingerprints on the light, absorbing specific colors that correspond to different molecules. Instruments aboard space telescopes can separate the light into a spectrum and identify the missing shades. These missing pieces reveal which gases are present. Even if the planet itself remains hidden in darkness, its atmosphere announces itself in these tiny shifts of color. Another method involves watching the planet as it passes behind its star. When the planet disappears from view, the total light reaching the telescope decreases slightly. Measuring this change helps scientists determine how much infrared radiation the planet emits and how reflective its atmosphere might be. These techniques are subtle, relying on minute differences in brightness, but they offer a powerful way to probe atmospheric layers without ever touching them. Some atmospheres contain familiar gases. Hydrogen and helium often dominate the atmospheres of giant planets, much like Jupiter and Saturn. These light gases are common in young planets and can persist for billions of years. Water vapor, carbon dioxide, nitrogen, and methane are also frequently detected, especially on planets closer in size to Earth or Neptune. Each of these gases tells a different story. Carbon dioxide might indicate volcanic activity or a strong greenhouse effect. Methane could result from geological processes, or, more intriguingly, biological ones. Water vapor may hint at oceans, clouds, or a planet warm enough to sustain liquid water. Other planets possess far more exotic atmospheres. Some may have clouds made of metals or silicate minerals. On extremely hot worlds, the upper atmosphere may contain vaporized rock, titanium compounds, or aluminium-bearing molecules. These unusual gases point to conditions far beyond anything experienced on Earth. A planet so hot that its rocks evaporate must orbit very close to its star, and the presence of these gases reveals information about temperatures, pressures, and chemical reactions occurring high in the sky. An atmosphere rich in hydrogen might indicate a planet that never lost its early gases. A planet with little or no atmosphere could have been stripped by strong stellar winds. The presence of oxygen, though intriguing, is not a guaranteed sign of life. Oxygen can accumulate through chemical processes, especially on planets bombarded by ultraviolet light. However, oxygen combined with methane in steady amounts would be far more suggestive, because the two gases tend to react with each other unless something continually replenishes them. This is one reason astronomers search for combinations of gases rather than single components. The overall chemistry must make sense over long timescales. The thickness of an atmosphere plays a crucial role in shaping the climate. A thick atmosphere can trap heat, creating a greenhouse effect like the one on Venus. A thin atmosphere may offer little protection, allowing heat to escape quickly and causing extreme temperature swings between day and night. The pressure at the surface affects whether water can exist as a liquid and influences weather patterns. Even the color of the atmosphere can provide hints. A planet with a blue atmosphere might be scattering light through gases like nitrogen and oxygen, while a reddish or yellow atmosphere could indicate dust, organic hazes, or volcanic particles. Studying atmospheres helps scientists understand not just the present state of a planet, but also its past. A world with large amounts of carbon dioxide might once have had oceans that later evaporated, leaving behind a dense, dry atmosphere. A planet with little atmosphere may have experienced a catastrophic impact, or undergone a period of intense radiation that stripped its air away. The ratio of different isotopes within the gases can reveal ancient processes that shaped the planet over billions of years. These details allow astronomers to reconstruct a planet's history with surprising accuracy, almost like reading layers of rock on Earth. The behavior of an atmosphere also affects habitability. For life to thrive, a planet needs a stable climate and a protective layer of gases. The atmosphere shields the surface from harmful radiation, regulates temperature, and supports cycles of nutrients. A world with no atmosphere is exposed directly to space and unlikely to host surface life. A world with an overly thick atmosphere might be too hot, too pressurized, or too toxic. Understanding the balance of gases helps scientists evaluate whether any given planet could support biology. Astronomers are especially interested in atmospheres of rocky planets near the size of Earth. These atmospheres are more difficult to detect because they are thinner and produce weaker signals. However, modern telescopes are becoming sensitive enough to study them. When light passes through the atmosphere of a small rocky planet, even a faint hint of water vapor or carbon dioxide can provide valuable information about temperature and climate. Future observatories may be able to detect more subtle signatures, such as ozone, nitrous oxides, or other compounds linked to chemical cycles. One of the most remarkable things about alien atmospheres is how diverse they can be. Some planets have calm, thick blankets of gas that barely move. Others have fierce winds that carry storms around the globe. Some atmospheres are transparent, letting starlight pass clearly. Others are so cloudy that the surface cannot be seen at all. Some are layered like complex desserts, with distinct chemical regions stacked on top of one another. Others are uniform and simple, containing only a few stable gases. Despite this diversity, all atmospheres serve as windows into the nature of their worlds. They reveal information about mass, temperature, pressure, and chemistry. They show how planets evolve over time and how they interact with their stars. They even hint at the possibility of life by showing whether gases are in unusual or unstable combinations. Studying alien atmospheres allows scientists to bridge the distance between Earth and distant worlds. A tiny dip in starlight, a shift in color, or a faint glow in infrared can speak volumes about what lies beneath. Through these small clues, astronomers uncover the secrets of planets they may never see directly, piecing together stories of formation, change, and possibility. Atmospheres, delicate yet revealing, remain one of the most powerful tools in the search for life and the understanding of exoplanets across the galaxy. The search for Earth-like worlds begins with a simple question. What does it actually mean for a planet to resemble Earth? At first, the definition seems straightforward. An Earth-like planet should be similar in size, orbit a stable star, and sit comfortably in the habitable zone where liquid water could exist on its surface. It should have a rocky composition, not a thick layer of gas, and ideally possess an atmosphere capable of supporting a stable climate. But as astronomers study more exoplanets, the idea of what counts as Earth-like becomes more flexible. Nature produces planets in countless variations, and many may be suitable for life even if they are not perfect twins of our own world. To qualify as Earth-like in the strictest sense, a planet would need to match several key characteristics. Its size should be close to that of Earth, probably within a small range above or below. If it is too large, its surface gravity might become intense, affecting the thickness of the atmosphere and the behavior of water. If it is too small, it may struggle to hold onto an atmosphere at all. The planet would also need to orbit its star at a distance where temperatures remain moderate. Too close, and the planet risks becoming a scorching desert. Too far, and water freezes into permanent ice. In addition, the star itself should be relatively stable, not prone to violent flares that could strip a planet's atmosphere or bombard it with harmful radiation. When astronomers began looking for such worlds, they expected them to be rare. After all, the conditions that make Earth habitable seem remarkably balanced. Yet the more we learn, the more it appears that planets of roughly Earth-size orbit stars throughout the galaxy. Many small rocky planets have been discovered in the habitable zones of their stars, especially around smaller stars known as red dwarfs. These stars are more common than stars like the Sun, and their planets are easier to detect. Some estimates suggest that Earth-sized planets in habitable zones may exist around a significant portion of stars in the Milky Way. However, being Earth-sized and sitting in the right orbit does not guarantee that a planet is truly Earth-like. A world could be covered in thick clouds that trap heat, creating a Venus-like hothouse. It could be a frozen desert if it lacks a substantial atmosphere. It might have oceans too deep and too pressurized for rocky surfaces to exist. It could also be tidally locked to its star, with one side in constant daylight and the other in permanent night. None of these conditions prevent life entirely, but they change the nature of habitability. This leads to an important idea. A perfect Earth twin may not be necessary for life. Planets that differ from Earth can still offer suitable conditions for biology. A tidally locked world, for example, might have a habitable region along the boundary between day and night. A planet with thicker gravity could support an atmosphere that stabilizes temperature more effectively than Earth's. A world with more water could host rich oceans even if it lacks continents. The variety of potential life-supporting environments is far greater than the narrow template of Earth. Some of the most intriguing current candidates for Earth-like planets orbit relatively small stars. These planets are easier to detect because their transits block a larger fraction of the star's light. A few well-known systems have captured the attention of astronomers. One is a compact group of rocky planets orbiting a cool, dim star where several worlds appear to lie within or near the habitable zone. Their sizes are close to Earth's, and their densities suggest they are rocky. Although their atmospheres remain unconfirmed, they provide a tantalizing glimpse of how common Earth-sized planets may be. Another promising category includes planets slightly larger than Earth, but still within the rocky range. These worlds might possess more mass, allowing them to hold on to thicker atmospheres and maintain long-term volcanic activity. Depending on their orbits, they could support climates that are stable and mild. If they have oceans, the additional gravity might change how currents flow or how weather patterns evolve. These planets are not exact Earth copies, but they remain compelling candidates for habitability. When evaluating the potential of an Earth-like planet, astronomers look closely at the atmosphere. A thin veil of gases can reveal a great deal. Water vapor indicates that the planet may have clouds or oceans. Carbon dioxide provides hints about greenhouse warming. Methane, depending on its abundance, can suggest geological or even biological processes. Oxygen is especially interesting, though it must be interpreted cautiously. Only when atmospheric gases appear in unusual combinations do astronomers begin to consider biological explanations. The challenge is that atmospheres are difficult to detect on small rocky planets. Their signals are faint and easily lost in noise. But as telescopes grow more sensitive, the ability to study these atmospheres improves. Future missions may allow scientists to determine whether an Earth-sized planet has blue skies, thick clouds, volcanic gases, or even seasonal changes. Each detail helps fill in the picture of what the planet is truly like. The rarity of true Earth twins remains uncertain. it may turn out that planets with Earth's exact combination of atmosphere, geology, oceans, magnetism, and climate stability are uncommon. Or it may turn out that the galaxy is full of worlds with similar balances. We simply do not yet know. What is clear is that Earth-sized planets in habitable zones are far more common than once believed. The diversity among them is enormous, which means the galaxy likely hosts a wide range of worlds with unique and beautiful environments. The search for Earth-like worlds is not only scientific, but also emotional. It taps into a human desire to understand our place in the universe. When astronomers study a distant planet that resembles Earth in size or orbit, there is a quiet hope that somewhere across the galaxy, conditions may exist that allow life to flourish. These worlds remind us that Earth is not an isolated miracle, but part of a larger population of planets shaped by universal physics. The pursuit of Earth-like planets blends realism with wonder. The science is grounded in careful measurement, yet the possibilities stretch the imagination. Somewhere, perhaps on a small blue world circling a quiet star, life may have taken hold. Whether such a planet looks exactly like Earth, or simply shares some of its essential qualities, does not diminish the joy of the search. Each discovery, each new world, brings us one step closer to understanding how common life might be in the vast reaches of the cosmos. The future of exoplanet discovery rests in the hands of telescopes so large, so sensitive, and so exquisitely engineered that they will reshape our understanding of distant worlds. These megatelescopes, both on Earth and in space, are designed to collect light with unprecedented precision. They will allow astronomers to detect smaller planets, study fainter signals, and observe chemical signatures that have long been beyond reach. Each new generation of instruments brings with it a sense of quiet anticipation, a feeling that the cosmos is preparing to reveal secrets it has held tightly for billions of years. On Earth, the coming era of giant observatories will change astronomy in remarkable ways. These telescopes use mirrors that are many meters across, assembled from segments that fit together like petals of a vast gleaming flower. Their size allows them to gather far more light than previous instruments, capturing faint signals from distant stars and planets. With adaptive optics, they can correct for the blurring effects of Earth's atmosphere in real time, sharpening their view of the universe. The result is an image with stunning clarity, revealing details once considered impossible to observe from the ground. One of the most eagerly anticipated telescopes is a massive observatory that will rise in a remote high-altitude location where the air is dry and stable. When complete, it will be capable of detecting the subtle wobbles in starlight caused by Earth-sized planets. It may even be able to take direct images of some rocky worlds, separating their faint glow from the overwhelming brightness of their stars. These ground-based telescopes will not work alone. They will be supported by an international network of observatories, each specializing in different wavelengths of light. Together, they will form a coordinated system capable of tracking exoplanets with extraordinary precision. In space, a new generation of telescopes is also on the horizon. Space-based observatories avoid the distortions of Earth's atmosphere entirely, allowing them to collect light with perfect steadiness. These telescopes will study planets with unmatched sensitivity, focusing on the delicate spectral signatures produced by their atmospheres. Some instruments will be tuned specifically to detect water vapor, methane, carbon dioxide, and other key molecules associated with habitability. Others will search for faint glimmers of reflected light, revealing the color and cloud composition of alien skies. One particularly ambitious mission aims to observe planets by blocking out the starlight that hides them. This technique involves deploying an artificial shade, sometimes called a star shade, positioned thousands of kilometers away from the telescope. The star shade casts a shadow over the telescope, reducing the star's glare and revealing the dim planets nearby. If successful, this method could allow astronomers to capture direct images of Earth like planets around distant stars. Seeing such a world, even as a tiny point of light, would be a profound achievement. Improved sensitivity is one of the most transformative aspects of these upcoming instruments. Current telescopes can detect the atmospheres of large gas giants with relative ease, but small rocky planets produce much weaker signals. Next-generation telescopes will be able to measure these faint signatures, identifying gases in amounts that would previously have been undetectable. A planet only slightly larger than Earth could reveal water vapor in its sky, or a thin atmosphere of carbon dioxide. These discoveries will help scientists determine how common potentially habitable environments may be. Another breakthrough involves time. New telescopes will be able to observe the same planet repeatedly over long periods, watching how its atmosphere changes with seasons or rotation. A shift in brightness over time might reveal cloud patterns. Slight changes in spectral signatures could hint at weather cycles or chemical processes. By combining years of observations, astronomers will build far more complete pictures of distant worlds, moving beyond single snapshots into something closer to a living, dynamic portrait. Future instruments may even be able to detect surface features. This will not come in the form of detailed landscapes, but through subtle variations in reflected light. As a planet rotates, different regions will reflect different colors and intensities. Oceans, deserts, forests, and ice all scatter light in characteristic ways. With careful analysis, it may become possible to identify broad surface types on exoplanets, distinguishing between worlds dominated by water, rock, or vegetation-like environments. While this remains an ambitious goal, the principle is within reach. The next steps in exoplanet science also include collaborative missions. Telescopes on Earth will detect new candidates and measure their masses. Space-based observatories will examine their atmospheres. Other missions will search for transits, or use gravitational microlensing to detect planets that cannot be found by other methods. Together, these instruments will create a layered approach to discovery, revealing the same planet from multiple perspectives. The future also promises the ability to study planets around faint stars or stars obscured by dust. Infrared telescopes, cooled to extremely low temperatures, will detect the warmth emitted by planets that orbit far from their suns. Radio observatories may uncover signals produced by charged particles in planetary magnetospheres. Even planets drifting through interstellar space could become detectable as technology improves. Perhaps the most exciting possibility is that these mega telescopes will allow astronomers to identify chemical imbalances in planetary atmospheres that suggest biological activity. A planet where oxygen and methane coexist in steady quantities would require constant replenishment, something that life on Earth accomplishes naturally. Detecting such a combination across light years would not confirm life outright, but it would be one of the strongest hints humanity has ever received. As each new observatory comes online, the distance between us and distant worlds becomes just a little smaller. The universe grows clearer, more familiar, more detailed. With every improvement in technology, planets that once appeared as faint shadows begin to reveal themselves as fully fledged worlds with weather, chemistry, and histories of their own. Mega telescopes will not simply find more planets. They will help us understand them as living, dynamic environments rich with possibilities. In the quiet depths of space, unseen worlds wait patiently for these instruments to bring them into view, one gentle beam of starlight at a time. Planetary systems begin as quiet clouds of gas and dust drifting through space, illuminated gently by nearby stars. These clouds, known as nebulae, float in the galaxy for millions of years, held together loosely by their own gravity. Nothing about them seems hurried or structured. They appear soft and formless like cosmic fog. Yet within these clouds lies the potential for stars, planets, moons, and every world that will one day orbit beneath distant suns. The story of planetary formation begins with this stillness, long before any planet takes shape. A small disturbance is all it takes to begin the transformation. A nearby supernova explosion, a passing star, or the gradual tug of gravity can cause a region of the nebula to collapse inward. As the gas and dust fall toward the center, they spin faster, forming a swirling disk around what will eventually become a young star. This disk, thin and wide, resembles a cosmic whirlpool. Most of the material will flow inward, heating and compressing until a star ignites at the center. The remaining dust and gas continue to orbit, spreading out into a vast rotating plane. From this disk, planets emerge. Tiny grains of dust collide gently, sticking together through electrostatic forces. Over time, these grains grow into pebbles, then rocks, then larger bodies known as planetesimals. These early building blocks occasionally crash into one another, but far more often they merge, gradually forming larger and more stable masses. Gravity becomes the dominant force as these objects grow. The larger a body becomes, the more strongly it attracts surrounding material. Within a few million years, the disk fills with growing planets that sweep up debris as they orbit. Why planetary systems differ so dramatically from one another comes down to countless small variations in this early environment. A slight difference in temperature within the disk can determine whether water ice forms near a particular region. A tiny change in density can influence where rocky materials accumulate. Even the timing of collisions matters. Two young planets that collide early in the process may merge into a single world. If they collide later, when both have developed stable orbits, the impact could scatter material and create moons instead. Close to the central star, the disk is warm. Temperatures may be too high for volatile materials like water or methane to freeze. As a result, planets forming in these regions tend to be rocky, composed of metals and silicates. Farther from the star, the disk becomes cooler. Here, ices can form, providing additional material for planetary growth. This is why giant planets often form in these colder regions. With both rock and ice available, they can grow quickly, becoming large enough to capture thick layers of gas before the disk dissipates. The gravitational dance among forming planets shapes the system in profound ways. As planets grow and move through the disk, they create waves in the surrounding gas, altering the orbits of nearby bodies. These interactions can cause planets to migrate inward or outward. A newly formed gas giant, for example, may drift closer to the star, pulling smaller planets along or even ejecting them entirely. Other planets might be nudged into eccentric orbits, tilted or elongated as they respond to the gravitational influence of their neighbours. The result is a dynamic shifting system where planets are constantly adjusting their paths. In some systems, planets settle into stable patterns with evenly spaced orbits. In others, gravitational resonances lock planets into rhythmic cycles, where their orbital times form simple repeating ratios. These patterns, once established, can last for billions of years, but the early period remains chaotic. Dust, gas, and infant planets collide, merge, or scatter as the system gradually clears. The young star begins to burn brightly, releasing strong winds that sweep away the remaining gas. What remains is a collection of planets, moons, and debris that will orbit the star for the rest of their existence. The early history of a planetary system determines much of its future. A planet that forms quickly near the star may never have the chance to grow into a gas giant. A world that forms late may be too small to hold onto its atmosphere. A young planet in a crowded system may experience violent collisions that reshape its surface or change its composition. Even the presence of neighboring stars can affect a system's evolution. A binary star system, for example, may produce planets with unusual orbits, shaped by the gravitational pull of two suns. Some planets inherit atmospheres from the gas-rich disk around them. Others develop atmospheres later through volcanic activity or chemical reactions. The thickness and composition of an atmosphere influence climate, weather, and habitability. A world rich in carbon dioxide may become dangerously hot. A planet with a thin atmosphere may cool too quickly. These conditions are determined largely by the early development of the planet and the materials it captured during formation. The diversity seen in exoplanetary systems reflects the enormous variety of conditions within these early disks. Some systems contain tightly packed inner planets, all orbiting closer to their star than Mercury orbits the Sun. Others have planets widely spaced. Some contain multiple gas giants, while others contain none. Some systems have planets that orbit at extreme angles, tilted drastically compared to the star's equator. These differences arise not from exotic physics, but from subtle variations in the initial conditions of the disk. Studying the formation of planetary systems helps astronomers understand why Earth exists in its particular form. The presence of Jupiter, for example, influenced the orbits of countless smaller bodies during the early days of the solar system. Its gravity protected the inner planets from some impact while redirecting others. The early collisions that shaped Earth, including the giant impact thought to have formed the Moon, were direct results of this chaotic formative period. Every solar system carries the imprint of its birth. The structure, composition, and orbits of the planets reflect the environment of the early disk and the complex gravitational interactions that followed. By studying how these systems begin, astronomers can trace their evolution through billions of years, building a deeper understanding not only of distant worlds, but of our own place in the cosmos. Planetary systems may appear calm and orderly today, with planets following predictable paths around their stars. But their origins tell a different story, one of dust clouds collapsing, young stars igniting, worlds colliding, and gravity weaving the architecture of entire systems. This early chaos gradually settles into the stability observed today. And within that stability, planets evolve into the diverse and beautiful worlds scattered across the galaxy. Life as it might exist elsewhere begins with the simplest of questions. What does life truly need? When stripped down to its basic physical requirements, life appears wonderfully flexible. It needs a source of energy, some form of chemistry capable of building complex molecules, and a stable environment where those molecules can assemble, persist, and evolve. On Earth, liquid water provides the setting for this chemistry. Sunlight or chemical reactions supply energy, and the planet's atmosphere and oceans offer stability. But these conditions are not unique to Earth, nor are they the only possible foundations for life. The universe contains countless environments where energy, chemistry and stability occur in forms very different from those familiar here. One reason alien life may not resemble life on Earth is that Earth itself represents only a single example among an unknown range of possibilities. Our biology uses carbon as its fundamental building block, water as its solvent, and DNA as the carrier of information. But this arrangement arises from Earth's particular conditions. In other environments, different chemistries might become favourable. Some scientists explore the idea that life could use methane or ammonia as solvents, especially in extremely cold worlds where water is locked in ice. Others consider the possibility of exotic polymers forming the basis of living structures. While these ideas remain speculative, they remind us that biology is a product of environment, not a universal template. Consider a planet with a thick atmosphere of methane and nitrogen orbiting far from its star. Such a world would be cold, its surface frigid, its lakes filled not with water, but with liquid hydrocarbons. Yet even here chemical reactions can take place. Slower, perhaps, than those on Earth, but still capable of forming complex molecules. If life were to emerge in this environment, its structure and behavior might differ dramatically from earthly organisms. It might move slowly, process energy at a glacial pace, and use chemical pathways alien to human understanding. Still, it would meet the basic requirements of life: energy, chemistry, and stability. On the opposite extreme are planets where heat dominates. A world orbiting close to its star might have temperatures high enough to melt metals, yet at certain depths or in sheltered regions, cooler layers could exist. Life that thrives in extreme heat on Earth provides small hints about what might be possible. Microbes have been found near hydrothermal vents, where water temperatures exceed hundreds of degrees. These organisms use chemical energy from the planet's interior rather than sunlight. If similar vents exist on ocean worlds or on planets warmed by tidal heating, life could form around them. The organisms might never see the surface, living entirely in darkness, nourished by minerals and heat. Gas giants present another interesting possibility. Though they lack solid surfaces, their atmospheres contain layers with temperatures and pressures suitable for complex chemistry. Some researchers imagine life existing as floating organisms, shaped by the surrounding gases, drifting on currents like jellyfish in a vast aerial ocean. These creatures, if they exist, would be adapted to constant motion. They might draw energy from sunlight penetrating the upper layers, or from chemical reactions deeper down. Their forms could be spherical, filamented, or amorphous, shaped by the buoyant environment rather than by gravity acting on solid ground. One of the most scientifically grounded possibilities involves subsurface oceans. Moons and planets with icy crusts can hide liquid water beneath, kept warm by internal heat. These oceans may persist for billions of years, forming stable environments completely shielded from the harshness of space. If hydrothermal activity occurs, life could emerge and evolve without ever needing sunlight. This possibility is supported by Earth's deep-sea ecosystems, where vibrant communities flourish in total darkness. If life can thrive in these hidden places here, similar ecosystems might be waiting in the oceans of distant worlds or rogue planets wandering the galaxy. Another important concept is adaptability. Life on Earth has shown remarkable resilience, colonizing environments once thought too extreme. It thrives in acidic lakes, alkaline springs, freezing deserts, and intense radiation. It survives crushing pressures on the ocean floor and near boiling temperatures in volcanic springs. These examples reveal that life is not fragile. It adapts. It evolves to suit its environment. Alien life shaped by the conditions of its world may be just as adaptable. It might rely on chemistries that seem improbable to us, simply because we lack the direct experience of those worlds. Imagining alien life requires balancing creativity with scientific grounding. It is tempting to picture fantastical creatures with dazzling forms, but the most compelling possibilities arise when imagination stays tethered to physics and chemistry. For instance, life that relies on photosynthesis under a red dwarf star might appear dark or even black, optimized to absorb long wavelength light. Life on a tidally locked planet could migrate around the twilight zone between day and night, following the region where temperatures remain moderate. Organisms might evolve reflective surfaces to protect themselves from intense starlight, or insulating shells to endure long periods of darkness. Some life might not be multicellular at all. Microbial ecosystems could dominate most inhabited planets. While microbes are small, they are extraordinarily diverse. They shape their environments, cycle nutrients, and build complex relationships. If life exists elsewhere, it may persist quietly in oceans, soils, or subsurface layers, influencing its world without leaving grand visual signatures. Yet even microbial life would be a profound discovery. It would show that biology is not unique to Earth, and that the universe offers multiple paths to complexity. The search for signs of life focuses on detecting chemical imbalances in planetary atmospheres. Life alters its environment in measurable ways. On Earth, photosynthesis produces oxygen, while biological processes maintain a balance of gases such as methane. Observing similar patterns in an exoplanet's atmosphere could hint at life. Scientists must be cautious, however. Some chemical combinations can arise through non-biological processes. The goal is to identify patterns that are difficult to explain through geology alone. The beauty of imagining life elsewhere is that it expands our sense of possibility. It encourages humility, reminding us that Earth's familiar biology is only one example. It inspires wonder as we consider how life might adapt a world with two suns, endless oceans, frozen crusts, or dense glowing atmospheres. And it grounds us in science by showing that even the most imaginative scenarios must follow the laws of nature. Life as it might exist elsewhere is not limited to creatures that look like us or live as we do. It may be simple or complex, slow or rapid, delicate or resilient. It may be hidden beneath ice, drifting through gas clouds, swimming in methane lakes, or clinging to mineral vents deep underground. Whatever form it takes, its existence would confirm something gentle and profound, that the universe allows for many interpretations of what it means to be alive. The search for distant worlds is not driven only by science. It is also shaped by something quieter and more personal, a long-standing desire to understand our place in the universe. For as long as people have looked at the night sky, they have wondered what lies beyond the glow of familiar stars. Ancient stories imagined gods, spirits, or distant realms. Later thinkers pictured other Earths, other lives, and entire worlds hidden behind the darkness. Today's search for exoplanets is a modern expression of the same curiosity, shaped by telescopes instead of mythology, but rooted in that same human longing to know what lies beyond the horizon. Looking outward into the cosmos is one of the gentlest forms of exploration. It asks nothing of the worlds it discovers. It does not seek to conquer them or change them. Instead, it simply tries to understand them. Each new planet adds a small piece to a puzzle that humanity has been assembling for generations. The question of whether Earth is typical or unusual, whether life may exist elsewhere, and how the universe chooses to arrange its worlds. The answers to these questions do not change daily life, but they reshape how people think, offering a broader and more calming sense of scale. Exoplanets help people understand that the universe is filled with possibilities far beyond the boundaries of Earth. Knowing that there are planets orbiting every kind of star, from hot blue giants to faint red dwarfs, changes the way one views the night sky. Instead of seeing a distant point of light, one begins to imagine entire systems, planets circling quietly, moons drifting through shadows, atmospheres swirling in gentle or dramatic patterns. These worlds exist whether anyone sees them or not, and that knowledge brings a subtle sense of peace. The universe is rich and busy, even in places where human eyes will never look. There is a comforting humility in realizing that Earth is only one world among countless others. Even the most extraordinary features of Earth become part of a larger picture. Oceans, mountains, winds, and clouds are not unique to this planet. They appear in varied forms throughout the galaxy. Some worlds have deeper oceans, some have thicker air, some have winds that move faster than sound. In this sense, Earth becomes both special and ordinary. It is a home shaped by familiar physics, following universal rules, participating in the cosmic dance that creates worlds in every corner of the sky. The search for exoplanets also reveals something about human nature. People are naturally curious. They enjoy learning about things they may never touch or experience. This curiosity is not driven by usefulness but by wonder. It is the same impulse that leads someone to turn over a seashell on a beach or to watch birds migrating across the sky. Discovering new planets satisfies a deep internal urge to explore, even from a distance. The exploration happens through light and mathematics rather than through footsteps, but the spirit behind it remains the same. Interestingly, the act of searching often matters more than the discoveries themselves. Each new exoplanet is exciting, but the knowledge that there are more to find creates a sense of ongoing adventure. The universe becomes a place with no real boundary, an endless expanse offering new mysteries at every scale. Even if humanity never visits these worlds, simply knowing they exist enriches the imagination. They become part of the human story, quiet companions in the night sky. Exoplanets also help broaden perspectives. When people consider the vast number of worlds beyond Earth, everyday concerns briefly feel smaller, more manageable. This is not escapism, but a gentle reframing, a reminder that life unfolds on many levels at once. The stars continue burning, planets continue orbiting, galaxies continue drifting. The universe holds steady regardless of the noise and rush of daily life. This larger view can be calming, offering a sense of place within a much bigger structure. The search for life beyond Earth adds another emotional layer. Even the possibility that simple microbes may inhabit a distant ocean inspires a kind of quiet awe, not because they would change life here, but because they would show that biology is not a rare accident. To discover life elsewhere would mean that the universe is not empty, but filled with its own creativity. Even without such a discovery, the act of searching encourages patience, reflection, and an appreciation for the subtle signatures that living worlds might leave behind. Astronomers often say that studying exoplanets teaches humanity as much about itself as about the cosmos. When imagining life on other worlds, people think about what life needs, how it adapts, and what it means to flourish. Thinking about distant planets highlights the fragility and resilience of Earth. It reminds people that their home is part of a larger system, influenced by cosmic events and governed by universal laws. The search also bridges cultures. People everywhere, regardless of background, can look at the night sky and share the same questions. What is out there? Could life exist elsewhere? Are there other worlds like this one? These questions belong to everyone. They encourage a sense of unity, reminding people that they share a single planet orbiting a single star, moving through a universe that is far larger than any individual concern. Above all, the search is an expression of hope, not the loud kind of hope that seeks dramatic change, but a quiet and enduring one, the hope that the universe is full of wonders still waiting to be understood, the hope that curiosity will continue guiding human thought long into the future, the hope that simply knowing about distant worlds enriches life here. In the end, the search for exoplanets is less about finding a place to go and more about expanding the space within the human mind. It opens new doors, invites new questions, and reminds people that discovery can be an act of gentle admiration. The universe does not need to reveal all its secrets at once. It simply needs to offer enough mystery to keep the spirit of exploration alive. The universe has a gentle way of reminding anyone who studies it that discovery is not a destination, but an ongoing process. Each time astronomers find a new world, measure a new atmosphere, or glimpse a faint signal from a distant system, they uncover more questions than answers. A planet thought to be simple reveals unexpected chemistry. A star assumed to be ordinary hosts a family of strange and beautiful worlds. A small shift in starlight raises mysteries about weather patterns, magnetic fields, or hidden oceans. The frontier of exploration keeps expanding, not because the universe resists understanding, but because it offers so much to observe, piece by piece, patiently and quietly. This endlessness does not feel overwhelming. Instead, it is calming. The universe presents itself in layers, allowing each step to unfold at a gentle pace. Humans explore tiny fractions of the cosmos, yet each fraction feels rich, complete, and meaningful. There is no need to rush through discoveries when even a single planetary system can keep scientists engaged for a lifetime. The idea that there is always more to learn becomes comforting. It ensures that curiosity never runs out of space. The sky remains a companion, full of possibilities rather than full of pressure. The vastness of the universe might seem intimidating from a distance, but when approached through the lens of exoplanets, it becomes soothing. Each planet, star, and system is a small, self-contained world, following its own rhythms and shaped by familiar physical laws. Even when the conditions are extreme, the underlying principles are stable and patient. Gravity acts steadily, atmospheres shift slowly, and orbits unfold in graceful arcs across unimaginable distances. The cosmic scale softens into something peaceful, a reminder that the universe has been here long before humanity arrived and will continue long after, carrying on quietly without demand or expectation. The more worlds astronomers discover, the more they realize how varied the universe truly is. There are planets of endless oceans, scorching giants locked in tight orbits, drifting wanderers travelling between stars, rocky siblings of Earth, and worlds where exotic elements fall as rain. No two systems look exactly alike. Each arrangement reflects its own history, shaped by early collisions, wandering migrations, and the slow sculpting of gravity. This diversity ensures that the frontier of discovery is not just endless in size, but endless in character. Every new planet adds texture to the tapestry, offering its own lessons about what a world can be. Perhaps the most serene idea in all of exoplanet science is that exploration is never meant to be finished. The cosmos does not present a final goal or a checklist to complete. Instead, it invites a way of thinking where questions are welcomed rather than feared. If a discovery answers one question, it naturally inspires several more. This gentle cycle mirrors the curiosity found in everyday life. The more someone learns, the more they notice what they do not yet understand. The joy comes not from reaching the end, but from being part of an ongoing journey. Technology will continue to improve. Telescopes will grow larger, instruments more sensitive, data more detailed. New techniques will reveal atmospheres that were once invisible and surfaces that were once mysterious shadows. But even as clarity increases, the universe will remain full of surprises. A planet that appears quiet in one spectrum may burst with activity in another. A star thought to be stable may flicker with subtle variations. A familiar category of planet may reveal a rare exception. The frontier expands not only outward, into space, but inward, into depth. This idea of an open-ended frontier mirrors the experience of looking at the night sky. No matter how often someone gazes upward, the stars never repeat themselves quite the same way. Clouds shift, seasons change, constellations rise or fall, and yet the overall view remains familiar and steady. In the same way, exoplanet discoveries shift and evolve, each one part of a wider picture. The quiet constancy of the cosmos acts as a backdrop for endless exploration. There is also a peaceful acceptance in knowing that humanity will never see everything the universe contains. Even with perfect technology and unlimited time, the cosmos is too large and too rich. But this is not a loss. It means that the universe will always hold something beyond reach, something unknown and unobserved, waiting patiently in the dark. The knowledge that the universe contains more worlds than can ever be counted creates a sense of spaciousness rather than scarcity. There is room for wonder on scales far larger than a single lifetime. As the search for exoplanets continues, the frontier of what is knowable expands gently outward. With each new discovery, the universe becomes both larger and more intimate. Worlds trillions of kilometers away feel closer through the light they share, the rhythms they follow, and the physics that shape them. The more that is learned, the more familiar the cosmos becomes, transforming distant points of light into dynamic places with their own skies, seasons, and stories. This endless frontier leads naturally toward reflection. It invites people to pause, breathe, and consider their own place within a universe that is vast but not indifferent. The cosmos does not ask for urgency. It offers quiet companionship, allowing humanity to explore at its own pace. Each exoplanet discovered adds a whisper to the chorus of worlds, reinforcing the idea that the universe is not empty and silent but full of gentle complexity. And so the search continues, not toward a final destination but toward a deeper appreciation of the vastness that surrounds Earth. The frontier remains open, calm, and welcoming. It invites curiosity without pressure and wonder without end. In this space of infinite possibility, exploration becomes less about arriving somewhere new and more about experiencing the simple joy of uncovering one more small truth about the universe. In the quiet drift back from deep space, it becomes clear just how many worlds we've visited in thought. Not physically, of course, but through light, imagination, and the soft guidance of science. Across these chapters, the universe opened gently, revealing its planets not as distant curiosities, but as places shaped by familiar forces, each following its own patient rhythm. We move through silent expanses where stars shine across impossible distances, We lingered beside worlds glowing with heat, worlds drowning in water, worlds lit by multiple suns, and worlds wandering alone through the darkness. And with every step, the cosmos felt less like a cold mystery, and more like a vast, serene landscape, full of calm variation and endless possibility. What began as a search for exoplanets gradually became something larger. It became a way of understanding our own connection to the universe. The science behind these worlds, transits, atmospheres, chemical signatures, orbital dances, provides structure, but the wonder comes from knowing that each world continues quietly on its path, whether or not anyone notices. A storm on a hot Jupiter does not wait for a telescope. An ocean beneath an icy crust warms and circulates even if no eyes ever see it. Light leaves distant stars long before it reaches us, carrying the faintest traces of their planet's stories. The universe moves with or without an observer, and there is a quiet comfort in that constancy. Along the way, we explored how planets form, how they migrate, how they shine or hide, how they warm or freeze, and how they evolve across billions of years. None of these processes rush. Gravity works slowly. Dust gathers patiently. Atmospheres shift with gentle persistence. The universe prefers calm repetition over haste, and that rhythm gives every world, every exoplanet, every star, every drifting particle of dust, its own soft character. Even in the most extreme environments, you can sense the underlying order, the stable physics guiding each moment. Earth begins to feel both familiar and extraordinary when viewed through this wider lens. So many planets in the galaxy share features with Earth: oceans, weather, atmospheres, heat, seasons, even the potential for life. Yet Earth is also distinct in its balance, its history, its long stability. Instead of standing apart, it becomes one expression of a universal style of creation, a single verse in a cosmic poem written across billions of light years. Looking outward helps clarify how special Earth is, not because it is the only habitable world, but because it is ours. There is also something deeply soothing in realizing that humanity is not standing on the edge of a small, limited space, but within a vast continuum. The search for exoplanets is an exploration without borders. With every new telescope, the frontier extends a little farther. With every faint detection, the universe becomes slightly more familiar. This kind of exploration asks for no urgency. There is no race against time, no finish line. Just an open sky and the human desire to understand it gently and patiently. The possibility of life elsewhere threads through this journey like a quiet hope. Not a hope for dramatic revelations or alien encounters, but for the simple affirmation that life, in any form, might not be alone. If microbes swim in hidden oceans on distant worlds, or if chemical networks stir in methane lakes beneath dim suns, their existence would be enough to reshape our sense of belonging. The search for such life is an act of humility, a recognition that the universe is too vast to assume Earth holds its only spark of biology. And yet, even without proof, the search itself is meaningful. It invites a kind of peaceful curiosity. It asks us to imagine without forcing conclusions, to observe without needing mastery, to appreciate scale without feeling lost in it. The unknown becomes not a source of fear, but a place of openness, a calm horizon, a quiet room waiting to be explored at leisure. As the journey winds gently back toward home, the exoplanets we visited in thought fade into the distance. Their atmospheres, oceans, storms and shadows slip into memory, leaving behind a softened sense of perspective. When you look at the night sky now, the stars may feel a little fuller, each one holding the possibility of entire families of worlds. You might picture planets drifting in their orbits, clouds swirling above alien landscapes, or oceans shimmering beneath distant suns. You may feel the faint awareness that the darkness between stars is not empty, but full of hidden stories. This awareness brings a unique kind of comfort. The universe is vast, but it is not unfamiliar. It follows patterns that can be understood, rhythms that can be traced, and laws that can be trusted. It gives freely of its light, whispering clues across unimaginable distances. And even though it remains filled with mystery, those mysteries feel gentle. They feel open, patient, and ready to be discovered whenever curiosity reaches out. The beauty of the unknown lies in its ability to make the present moment feel spacious. You do not need to solve the cosmos to feel at ease within it. Simply knowing that countless worlds drift quietly through the dark can be enough. They continue turning, orbiting, and evolving regardless of attention. They exist without demanding interpretation. And in that quiet independence, they offer a reminder that discovery is not a burden, but a gift. As this journey comes to a close, the universe does not shrink behind you. It remains as wide and peaceful as ever, stretching softly in every direction. The stars continue their glow, the planets maintain their orbits, and the frontier stays open, endless, and unhurried. You carry the calm of that space with you, knowing that the universe is vast, welcoming, and full of gentle mysteries still waiting to be found.